Hi there, everyone. Welcome back. If you got through the first 40 minutes of the first exercise, then well done. And obviously, you've got the practice as well. We're about to do the second exercise from the book. So this is Unit 1, about sequences and series at the moment. And they're cracking through a lot of topics, little mini topics, really quickly. So we're actually going to deal with both arithmetic and geometric sequences and series. I think this goes over a couple of exercises, but there's a lot of ideas put into 1B. We're going to deal with the questions for 1B. I've microwaved my tea as well because I didn't finish that. I've just spent about an hour making videos so far. Okay, right, let's get straight on with this then. So arithmetic sequences, sometimes called arithmetic progressions. Let's get rid of myself again. We're talking about growth represented by a linear relationship. So for example, things could go up in 2s or 3s or 4s or whatever, but basically there will be a common difference every time. Here we go, let's have a little look. Sometimes this is called a arithmetic progression, which I talked about. Interestingly, they also talk about recursive definitions. So they're chucking a lot of stuff at you already here. And they're saying in this case, so recursive or iterative definition means how do you get from one term to the next term, not how do you get from the term number to the term itself. So a general term would take you from, I don't know, I'll give you n is 100, and you'll need to give me the 100th term. Whereas a recursive equation is if I say to you, well, here's the 99th term, what's the 100th one? That's a recursive definition. So that's was worth looking. Just snatching that for a second. Just take this, because that can turn up a fair bit. So it will say un equals, in this case, un minus 1 plus d. And that's for an arithmetic progression or an arithmetic sequence. We used to call arithmetic progressions APs. So we're talking about APs and GPs at the moment. Okay. So this is talking about the recursive definition for an arithmetic sequence. And so what we're talking about here is, say, for example, if I told you the 99th term was, I don't know, let's say 129. I don't know what it is. And then to get to the 100th term, for example, we'd say the previous term, which would be the 99th one, plus the common difference. So, for example, if the 99th term was, I'm just making this up, okay, 297, and the common difference is 3, that would be taking us to our 100th term, which would be 300. Okay, which would in fact be defining the 3 times table in that case. Okay, that might turn up later. Okay, let's just forget about that for a bit. So you can see, we've talked about this already in the first video. This is the general formula, and they've built up the same way as I've done in the first video as well. Okay, so the general term here is un equals the first term plus n minus 1 lots of the common difference. Now, remember, if you've got, I don't know, let's go 2, 5, 8, 11 is going up in 3, so there's an arithmetic sequence. If we're adding on, if we want to get to the 4th term, we'll need to add on 3 lots of the common difference there. So to get to the 4th term, we add on 3 lots of the common difference. There are 3 gaps essentially, and the gaps represent the common difference in each case. Okay, so let's just crack on straight away with the questions. Again, if you're sort of bored with my little bit of explanations from the book, or if you've ever read the explanations from the book already, then go straight to the examples which you are likely to struggle with or need a bit of help with. Okay, example 6 in this exercise, in this unit. So the 4th term of an arithmetic sequence is 18, and the common difference is minus 5. Determine the first term and the nth term. Well, they want us to use this formula. So they call AU1, depends what you want to call it. just my first term. So we're going to use this formula here. So the fourth term of an arithmetic sequence is 18. So U4 is 18. And we've got A plus 4 minus 1. So I'm just doing a substitution there. So plus 3 times by, it says the common difference is minus 5. Okay, so I can put in minus 5 there. Determine the first term and the nth term. Okay, so I can now solve this to work out A, the first term, or U1 if you like. And so what have I got? I've got 18 plus 15, I think. So A is going to give me 33. Okay, so the first term, U1, perhaps I should write down U1 to be explicit, is equal to, what did I say it was? 33. Okay, that's clearly me just taking the minus 15 to the other side and making plus 15. Okay, and so there's the first term, and the nth term is un equals a, which is 33, plus n minus 1, lots of the common difference, is minus 5. Now, it is good practice to multiply that out and simplify it, of course. So we can see that we're getting here, what's that? We're getting 33 minus 5n plus 5 there if we multiply out those brackets. So we can see we've got 38 take away 5n. Okay, there we go. First example done. Might be a bit quicker this time. Example 7. Okay, example 7. Find the number of terms in the following arithmetic sequences. Well, they stop at the nth term. So if this is the first term, this is the nth one, and n will define the number of terms in the sequence. So all I really need to do is use un is equal to the first term plus n minus 1 lots of the common difference, which is 3 in this case. And the nth term, we're looking for how many terms there are, we're looking for n. But the nth term in this case is going to be 83, that's where it's going to stop. So n is often used as the last term. And if they want any term, they might use UR. And that might be different to how you've used it at GCSE or any preceding course. Okay, is equal to 20 plus n minus 1 times by 3 again. Multiply that out. Being a bit slow here today. 3n minus 3. So we've got 17 here plus 3n. We've got 83. 83. We can take off the 17. What's it taking us down to 66 equals to 3n. Divide by 3 will give us the 22 terms. You can do exactly the same for the next one as well. I mean, there's nothing particularly interesting in these examples. But you can do the same for the next one. Again, you can set up minus 30 is equal to our nth term here. We've got 34 plus n minus 1 times by the common difference is minus 4 in this case because it's going down and forth. And you can solve that equation. If you can't solve that equation, you shouldn't be listening to these videos. Okay, so that is definitely easy for you to be able to do. Okay, and for the last ones here, again, we can set it up in a similar way. We've got minus 22a is equal to 6a plus n minus 1 lots of the common difference. The common difference is going down into 8 this time, so we can times by 2a. Now, I imagine that the a is going to cancel there at some stage, and anyway, you can solve that equation. It might give you an answer in terms of a. In fact, I don't think it does. I think if you just cancelled out the a's here, it would still give you the same number of terms. So the a should cancel out there, and yeah, you should get the number of terms. Right, let's have a little look at that answer. Yeah, there we go. You should have got 15, so 22, 17, and 15 there. Okay, right, let's look at 8. We are cracking through this time, but we're going to come unstuck in a bit because we're going to need a proof for the sum of an arithmetic sequence. So in other words, the formula for an arithmetic series is coming up. So, right, anyway, let's look at this. 3 numbers are consecutive terms, so in a row. You know, for example, consecutive numbers would be 2, 3, 4. Consecutive odd numbers would be 3, 5, 7. Or likewise could be 7, 9, and 11. Okay, so 3 numbers are consecutive terms of an arithmetic sequence. So we've got A plus D, and A plus 2D. Those are our 3 terms. The sum of the 3 terms is 45. Oh, right, okay. Sum of those is 45. And their product is 3,240. Oh, it's a nice question, this one. Okay, so if we times these 3 things together, then we get the answer of 3240. Okay, well, we might need to simplify that first line. So we've got 45 equals 3a plus 3d. Divide throughout by 3, and we're going to get 15a plus d. Oh, that's interesting. I'm basically just playing a little bit with this one. Just sort of setting it up and then playing with it. You can see that we've got here a plus d, and I just happen to notice that that's the same thing here. So I might substitute that one in. Yeah, okay. So basically I've got simultaneous equations though. And I mean, I could do it in different ways. I just noticed that I could substitute in the a plus d there. But I mean, I've essentially got simultaneous equations. So let me use the second equation. I should really give a bit more structure to these things. So this was the first equation. And if we go back to the second equation, let's just explain the examiner what's happening. Now I've got a times by 15, 15 at the front, 15a. Oh, my calculator. Let's just do a 3240 divided by 15. That's 216. Okay, so that's 216 when I divide by 3, and that's a plus 2d. You see what's happening here? A plus 2d there. Okay, that's plus in the middle. Okay, so I've got this equation here, and now I can essentially use this equation and this equation. I can substitute in, let's say, I don't know, a is equal to, so a is equal to 15 times d, and substitute in for the 2 times where we see a here. Thing is, I might actually just notice that here is another a plus d, but plus another d there. So that's the same as a, and then a plus d is 15 plus d. Okay, so I've just split that up into a plus d plus another d. And I knew a plus d was 15 already from over here. Okay, so now I've got 216 is equal to this. Now, obviously, if I've got 2 terms and 1 equation, I can't solve that. I can only come up with answers, pairs of numbers which work. In other words, if I put this into, let's check it out, let's do this. Okay, let's do something a bit more fun. If I put this into Desmos, right? So let's call a. Let's type that out. So what do we have? 216 equals. I'm just going to solve some simultaneous equations graphically here, okay? Rather than doing it here. So I've got 15 plus d. Oh, sorry, it only recognizes x and y, not a and d. So this is Desmos. Desmos is a really great tool to be playing around with. We can zoom out here. Let's get rid of that. I was playing around with it earlier. So there's the function. Interesting function. It's got an asymptote, 2 asymptotes, an asymptote there, and a horizontal asymptote, in fact. Okay, so let's have a little look. That was one of the equations, and the other equation was 15 equals x plus y. Okay, it looks to me like we have multiple solutions here. There we go, 12, 3. That's just a root there. Or a 0 to our function, and this one here is 18 minus 3. Okay, I can't remember which way around x and y are. Let's have a little look at this. So we can solve this. It should give us then a is equal to my x. So it should give us 2 sets of solutions. I'm cheating a bit here, of course. 12, 3, and 18 minus 3. So A is 12, D is 3. But there was another set of solutions, and we've got that other set of. I'm running out of space here. So the other set of solutions was when A is 18, D is equal to minus 3. Now, one of those solutions might be wrong. Let's just have a look at the questions. It says 3 numbers are consecutive terms of an arithmetic sequence. Well, if we assume that the numbers are going upwards, so they're consecutive terms going upwards, then this would be the answer there, 12 and 3. If they're going downwards, then the other set of numbers work. So let's have a little look. Let's see what they've done here. Oh, I mean they've solved. I mean they've solved the simultaneous equations. They've made it look very efficient. You can obviously play around with these things here. You've got this and this now. It's not too difficult to make a substitution of, say, A is equal to 15 minus D, and substitute that in there and then solve that equation. That's not going to be hard. It might turn into a quadratic that you can use your calculator for. Might be that you will have to use completing the square for it. You have techniques of solving quadratics, of course, coming into this course. Okay, anyway, I've used Desmos. That's what I did. Okay, anyway, so here's the answer. So we've got A is 12 and D is 3. Let's check out what the book is saying again. So they're saying D is plus or minus 3, which means that A was 12 if it was plus 3. Okay, when we substitute that back into one of the equations, they've used U, by the way, as the first term rather than A. So yeah, we're putting, when we had, let's go back to this, sorry about this. When we have A plus D is 15, when we had D is equal to 3, then we can say, well, our first term is 12, and then plus 3, and then plus 3. Okay, but if our first term instead from the other set of solutions is 18 and minus 3, obviously you'll get 18, 15, and 18, 15, and 12. So in fact, it's giving us the same solutions. They're the same set of solutions, but they could be consecutive going up or consecutive going down. Okay, making a bit of a meal of that one. If you find you've understood already, then just skip ahead. Let's skip on to the next one. Okay, example number 9. So the second term of an arithmetic sequence is 20, and the 7th term is 55. Okay, so it looks to me like we're going to get simultaneous equations in this case. So U2 is equal to the first term. U2 is going to be equal to 20, which is the first term, plus n minus 1 lots of D. But of course, the second term only has one common difference. Remember, of course, our terms are A plus D, A plus 2D, and so on. So our second term is A plus D. Okay, and the 7th term, so it's 55. So we've got our first equation, our second equation here. It's also going to be A plus 6 lots of the common difference, 6 gaps to get to the 7th term. And now we can solve those simultaneous equations. And you've been able to do that for years, I'm sure. So I'll let you do that. You can also do it on your calculator, on your Casio calculator. Right, what are we going to look at? Let's look at the next question. So there we go, they've solved their simultaneous equations. They're getting out, in that case, the first term is equal to 13, and D is equal to 7. Okay. Now, sum of an arithmetic sequence. I feel like splitting this into a second video, but at the moment I'm trying to stick to one video per exercise. But this would generally be another lesson in a slower course, but obviously our course goes really fast. So we really need a proof for this one, first of all, and here is the proof. This is a really nice proof. Let's just take a little bit of little square. I need to copy something in order to write on here. So I'm going to set this one up because I kind of enjoy this one. So the proof for the sum of an arithmetic sequence, well, for n terms. So we've got the first term is a. I'm not going to call it u1, I'll call it a. The second term is going to be a plus d. Okay, third term is a plus 2d, and we're going to go on all the way until the last term of a plus n minus 1 lots of d. Now the previous term to that would be a plus n minus 2 lots of d, but because I'm not going to have a lot of space for this, take that one out. I'd normally put that one in. Okay, so plus, 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 pluses, dot, 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 plus this thing on the end. This is the first term going up to the nth term, and this gives us what we're going to call the sum of the first n terms here. Okay, well, this is an infinite, potentially infinite expansion. We don't really know how many terms there are here. So we don't know what the dot, dot, dot is there in the middle. In fact, there could only be 3 terms, in which case we can stop there. But what we want to do is boil this down to one formula. Now, boiling this down to one formula is a kind of a trick to this. And what I'm going to do is write this now backwards. This is where I realize I should have left more space. Okay, that's a, and a n minus 2 lots of d, and then a plus minus 3 lots of d. So I'm just going backwards in one less lot of d, and then plus is all between these. So you see what I'm doing? I'm going from this end this way, writing it in reverse. I'm going to end with the final terms. I'm going to end with this, this, and this. So I've not got much space. I'm just going to write down plus a on the end. But I've written it in reverse. Now that's also Sn. It's the same thing as the thing above, just written in reverse. Now check this out. This is kind of clever. So this, when I add this together, it's going to give us the same as when we add this together. It's going to give us the same as when we add this together. Is going to give us, not with the dot, dot, dot. It's going to be a bit pedantic there. And then it's the same as when we add this together. They're all the same because I get 2a and n minus 1 lots of d. You can verify that from here as well. If I put d with n minus 2 lots of d, I get n minus 1 lot of d. Got 2 a's there. So I've got this n times over. You can check for each of those little bubbles I've made. You can see I've got that n times over. So I should put my n on the front. I'm going to just say n there, the end. There we go, that's my Sn. Oh, but it's not Sn anymore, is it? Because I've now added 2 lines together. So I've actually got to add 2 Sn. Okay, so Sn is now equal to n divided by 2. Divide by this by 2. The n to the front as well. And then I'm left with this thing, 2a plus n minus 1 lots of d. That is the formula for the sum of an arithmetic sequence for first n terms of an arithmetic sequence or an arithmetic progression. Now there's another version of this which is pretty nice. This. And instead of writing in the middle 2a plus n minus 1 lots of d, you can split that up into a plus this thing here. Okay, if you do that, you can see that a plus n minus 1 lots of d, this, the last term. See this from the first brackets that we've got a in the last term, but the first term and the last term. So we can split this up into the first term and the last term. So that also works as well. Sometimes that's a nice formula to use. Okay, right, good. That's really worth going through, really worth seeing if you can cover that up, hide it, and try and do it yourself. Let's have a little look at the questions then. There we go, this gives us this thing here as well. They're using U1 for the first time, by the way. Right, so what have we got to go through? We've got 4 more questions. Apologies for this. Let's see if we can make it relatively quick. 4 more questions. We've got question 10, 11, and 12 to get through. So, example number 10. I'll tell you what, my tea's got cold again. Can't keep microwaving it. Okay, example 10. First term of an arithmetic series is 5. Okay, the last term is 51. The series has 15 terms. Wow, that's going to be a really easy one because S of 15, sum of those 15 terms, is going to be 15n divided by 2. Remember the formula? The easier version of the formula was the first term plus the last term. First term is 5, last term minus 51. Just put that on there. I mean, you can get rid of the plus if you want to. And you can just type that into your calculator and press equals. Okay, easy. Second question. Sum of the series. Oh, sorry, what have I done that wrong? First term of an arithmetic series is 5. The last term is 51. The series has 15 terms. Find the common difference. No, I haven't done it wrong. That's fine. That's fine. It's just odd that they've asked us for the common difference when we can work out the sum of the series straight away. Okay, so well, we've worked out the sum of the series. That's what we just did. But the common difference you'll have to work out from UN. So, I mean, if your aim is just to work out the sum of the series, you don't need the common difference. Okay, so you can write down that the first term is 5. So UN is the last term, minus 51, equals the first term, which is 5, plus n minus 1. Lots of n minus 1 is 15, of course, so it's 15 minus 14 times by d. So in solving that, you can work out the common difference. They're trying to get you to do that because they're then thinking you might choose to use this formula. But why would you when you have the easier formula? This one here. Okay, so you can use that straight away for A. Phew, okay, well, I didn't make a mistake on that one. Let's just check the answers in case you're doing this separately. So let's look. The answers D were minus 4, and the sum of the series is minus 345. Okay, example 11. Do this one here. Okay, example 11. First term of an arithmetic series is minus 7. So here they've said arithmetic series. And the fourth term is 23. So we're definitely adding these things together. The sum of the series, okay, so they're letting us know that the series is going to be added together, but they're definitely saying the sum of the series give us the addition of all of them. So the fourth term isn't the addition of the 4. It's just saying the fourth one in our addition of the fourth thing that we need to add on. Okay. The sum of the series is 689. Find the number of terms in the series. Okay, well, first of all, we can say the fourth term, U4, is 23, the basic formula. UN is equal to the first term, minus 7, plus n minus 1, lots of D. I think we need to work out what D is. And by the way, n minus 1 is 4. 4 minus 1 there is so 3 by D. So that's just me setting up formula with UN, not SN at the moment. So let's add that on. We got 30. If we add the minus 7 onto the other side, so add 7 onto the other side rather. 30 divided by the 3 D is equal to 10. Okay, so pretty easy to see. So we've got the first term now. We've got the common difference. And we have the sum of the series. So this time around, we're given SN is 689 is equal to n over 2. We don't know what n is. And we've got 2a, so that's minus 14. Now, I'm always saving a bit of space here because I don't have much space to write on, but I'd probably actually write this down as 2 lots of minus 7. I'll be really explicit for the examiner and write down all my working out. But I'm trying to save a bit of space. In saving space, I will often make mistakes, as everyone does. Okay, and plus n minus 1. Okay, times by D, our common difference, times by 10 Right, okay. So I wonder if you know what type of equation this is. We have n on the inside, times by an n on the outside, or vice versa. Then we're going to end up with at least an n squared. In this, this is a polynomial or quadratic polynomial of order 2. Okay, so you can take steps now to solve this quadratic equation, or you might partially simplify it and put it into your calculator, because calculators, of course, do solve simultaneous quadratic equations. Most calculators, even the basic Casio, which you could use for GCSE or IGCSE, that would solve quadratic equations as well. There is a polynomial solver on our TI Inspire CX. There is a polynomial solver, or there's an n-solve on there as well. You've got lots of techniques for this. I'm not going to deliver a lesson now on solving quadratics, but from my point of view, I would tidy this up a little bit before taking it a bit further. So here we go. My mind's going a bit slow here. Times this by 2. Let's get rid of the divide by 2. 1378. 1378 times by n, and I'm going to swap around my terms in the center. We've got 10n in there, and then that was that minus 10 minus 24, and then we need to multiply this thing out. So we've got 10n squared minus 24n, take away 1378 equal to 0, and we can solve a quadratic equation. Before you solve the quadratic equation, perhaps divide it by 2 as well, makes it a little easier. But that looks like a difficult quadratic equation to solve. If you know the technique of solving quadratic equations in this form, you know the technique of saying a times c to start off with, and then thinking that whatever that number comes out to be, so it comes out to be 30, and thinking that yeah, if you know this technique, I should actually do it. And thinking that you're looking for two numbers that add the times together to give you minus 30, not necessarily those two numbers, and which add together to give you the plus b. If you know that technique is going to be difficult with this because the numbers are so high. So I might not do this technique here, although I suspect that it does factorize because n is a whole number. Looking for a whole number here. But I would probably use completing the square if I had to do this longhand, but otherwise I'd use the calculator. Let's check out what the book says. Oh, that's where I've got, in a lot of words, to like the fourth line of working out. They've divided by 2. They've factorized. The factorization here is really not nice. I don't expect that you would do it by that method. But then they say there's two answers here. Now, one of the answers is not going to be a whole number. So if you set that second bracket, let's just take, okay, so if you take that second bracket and try and solve that one equal to 0, because you have two things, either this one is equal to 0 or the other one is equal to 0. Now, you need an answer which is both positive, okay, and n is equal to this. This is negative, and it's not even a whole number, so that's definitely not going to work here. So I would put a big cross next to this solution. This one is good. This one is my final answer. Okay, right. Let's look at 2 more questions. We're nearly there. Okay. Right, example 12. Okie dokie, right. So example 12, find the value of this thing here, right? This thing here. It's much easier to say that. Okay, so if we put in 1, what do we get out? 5 times 1, take away 4, it's going to give us 1. Yeah, that's our first term. And if we put in 28, well, we can put in 2 if you want. 5 times 2 is 10, take away 4 is 6. I can see it's going up in 5s, but this is 4 less than the 5 times table. So the next one is 11, 16, and so on. These are our terms here. And the last term is when we put in 28 at the top. And when we put in 28 there, again, I apologize for being a bit of a dullard here. 140 take away 4, 136 is our final term. Now, if we need to just sum this together, this one's really easy. This is the sum of 28 terms. Really, we should have a plus in between here if we're defining a series rather than a sequence. Okay, but we're just adding together these things here. So all we need to do is 28 divided by 2. Remember, the easier version of this formula is the first term plus the last term. We know the first one. We know the last one. It's easy. Okay, last one. And last one here, example 13. And here we go. Sum of an arithmetic series is given by this formula here. Find the common difference in the first 3 terms of the series. Okay, well, this is really unusual the way this formula is given. But find the common difference. Doesn't mention D there. Find the first 3 terms of the series. Well, remember that S1 is just the sum of your first 1 terms. S2 is going to be the first term and the second. You can call that A if you want. I've just called it A2 here. And S3 is equal to U1 plus U2 plus U3. Find the common difference. Okay, so if I work out S2 and if I work out S1 and I find the difference between them, then I will be left with my second term. Okay, if I find the difference between these two, I'm just left with that difference. Okay, but of course S1 is equal to U1. So if I've then got U2 and U1, I can then find the common difference. So that's the strategy behind this question. Right, let's just get rid of all of that. So S1 in this case, when we substitute this in, we've got 1 times by 2 times 1, take away 3. So what's that? Minus 1, so that's minus 1. 1 is minus 1. And S2 is equal to, so let's put in 2 there. We've got 2 times 4, take away 3, which is 2. Saving a bit of space there, so that's 2. So remember that this is the first term, that's U1. This is U1 plus U2. So when I do S2 take away S1, I'm left with U2. And that's going to give me 2 minus minus 1, which is equal to 3. Okay, so now I've got U1 is equal to minus 1. And U2 then is running out of battery. Turn it off and on again. It's not liking it. Okay, U2. I'm glad this is the last question. Right, so U2, let's use the mouse. So U2 here is equal to, U2 is equal to, U2 is equal to 3. And so that means that the common difference here is equal to 4. Okay, because the difference between the first and the second term, which is 3, is now 4. And we're already told that this is defined to be an arithmetic series, so we don't need to go beyond to find U3 or anything. We're now done. So now we've got the first term sorted. We've got A is U1. Okay, we've got B is equal to 4. And we've got, do we have N? We were looking for S3, so we have N is equal to 3. And then we can substitute into our main formula again. Let's just check this one out because my pen is playing up. Here we go. D is 4. U1 is minus 1. U2 is 3. Well, you don't even need to use the formula here, do you? Because first term is minus 1. Add 4, you get to the next one. Add 4, you get to the next one. And then you can just add those 3 together to get S3. Okay. Right then, guys. Well, well done for listening so far. There's 15 questions in the next exercise. Obviously, get a copy of the book. My biggest recommendation to you. This is the Oxford book. This is just a PDF copy. In our school, we have all the online versions, of course. Okay, right. Well, crack on with that, and well done for listening, and we'll see you in the next video.